All right, dude, we are live. What's up, guys? This is Dem Keys, and today we're gonna be taking a slight detour from um, our usual Hugging Face, Transformers, and Kaggle study streams. We are still studying, but there was a bit of research that I was doing, which I kind of wanted to just continue on stream because I figured why not just stream it, you know? um i'm I'm anyways doing this research, and I could have paused it to then carry on doing transformers related stuff, but then I was like, why not just do it here? Hey Cutane, hello, welcome to the stream, and thank you for the lurk. We are doing yet another study stream, dude. I'm glad that I found this co-working and studying category. um I need to hang out in this category more. I've started streaming in this category, but I need to go and hang out more in this category, and maybe raid other people as well. Usually I would be streaming in software and game development, and I would raid people there. Now I want to try here. Actually, let me see if there are VTubers streaming in this category. Maybe later on whenever I do decide to raid. Um, I'm gonna check, but I mean, it doesn't have to be. It doesn't have to be only a VTuber, or rather, I should say, I'm not. I'm not opposed to raiding non-VTubers as well, but I want to see if there are VTubers streaming in this category. And there seem to be a couple actually. Oh yeah, dude. There seem to be a couple of people here. Hell yeah. Okay, anyways. So, we wait. Yeah. So, here's what I was doing. Let me just go back to the thing. So, I was chatting with Llama. I was doing some research on a couple of different things, which, well, it started with one thing, and then that led me to doing research on a couple of other things as well. Where should I begin? So okay, we can start with this. In stats, what is a distribution? And because like a bunch of these questions have already been answered for me, but I'm just asking the question again so that we can start reading from scratch, and like the LLM will have some more context of the conversation. Okay, in stats, what is a distribution, and what is a probability? Wait, did I spell that wrong? Probability. There. Probability distribution. Okay. I think I need to zoom in. Also, I think I can. Nah, I don't think I should do the full screen thing. Okay. Let's start by reading. Okay, so it's explaining both the things, so we can read both of them. Let me just zoom in so I can. Okay. Uh, right. In stats, the terms distribution and probability distribution are closely related, but can be distinguished as follows. A distribution, in a broad sense, refers to the way that the values of a variable are spread out or dispersed. Give me a second. Okay, yeah. So a distribution in a broad sense refers to the way that the values of a variable are spread out or dispersed. This can be described in terms of the frequency or density of the values. For example, you might talk about the distribution of heights in a population, which can be described by a histogram or a density plot. You know what? I haven't tried making a density plot. I've played around with histograms and I found actually a bunch of different use cases for them. Most recently, I found one very useful use case where trying to plot a histogram trying to plot a set of random values that were taken from a normal distribution, because they're random values and they're given to you like randomly, right? So they're not going to be in order at all. And so when you try to visualize it, it just looks like noise because they're random values and they're all over the place, right? What I wanted to do was kind of sort the values, but not really sort the values. It was more trying to group them into specific, well, groups. And that's kind of where histograms can help, because histograms work by binning the values. So they essentially group values into bins. Each bin is like a range of values. Each bin contains a range of values. And so when you try to plot a histogram out of noise, it kind of groups it up into these groups of values that are within specific ranges, which essentially sorts them. It in a way it sorts them, but not really sorts them. Well, kind of. It kind of sorts them. And then the bin itself, the bin bar that's being plotted, it's the bin bar is basically it's how often certain values are occurring. And so when I tried to plot that using a histogram, I was actually seeing a bell curve. So yeah, I've used histograms. I haven't used density plot yet, or maybe I have and I just forgot. I don't remember. I'm gonna have to see. Or a density plot showing the heights, showing how the heights are spread out. Actually, I'm curious. Hold on, is density plot a thing in Matplotlib? Because I think histogram is a thing in Matplotlib. I wonder if density plot requires Seaborn, or maybe stats models. Maybe stats models has it. Hold on. Yeah, Matplotlib. Matplotlib density plot. How to create a density plot? A much easier way to do this is to use Seaborn. Okay, got it. Don't need to tell me twice. So let's try. Let's try seeing if Seaborn has. Wait, histogram bins, density, and weights. All right, so I should probably look this up here. Give me a second. Let me switch to this and load up. Okay, so what am I looking for here? Matplotlib, density plot. Okay, so there's a Stack Overflow thing, and then there is, okay, so there's a link directly to Matplotlib as well. There's something for histograms. Let me also open up the, let me see what Seaborn has. Seaborn density plot. So there's a KDE plot, which is kernel density estimate, is a method for visualizing the distribution of oh my god, that was holy shit. Okay. So, well, sorry, what was I saying? Right. So I'm gonna open this up. Sorry, I'm watching Lena Lazar's stream on another screen, and yeah, just never mind. Right. So transition back, and all right. Wait, what's going on with this? Why is this not why is this not being displayed uh on the screen? Oh, there it is. Okay, cool. Right. Actually, give me a second. There is something that I have to do. Um, just real quick, I'm gonna do the thing and then I'll be good. Um, also need to do another thing somewhere else. By the way, I need to look into my middleware apps. What do you call it? I need to look into the token for my middleware app because I don't know. There seems to be something wrong because in the middleware app, it's not able to connect to the chat properly. It's it like connects and disconnects. Give me a sec. Yeah, so it kind of connects and disconnects, and because of that, it's just not reading anything. The same thing is for the reward system because I have a chat system and a reward system set up. Neither of them seem to be working, so I need to look into that. Now, give me a second, real quick. Let me finish this thing that I was trying to do, and then I will get back to you guys. Okay, we'll do that, and uh, this, and I think we are good to go. Oh, also, yeah. Okay, yeah, never mind. Um, yeah, cool, great. So now that that is done, we can get back to this. 5 years later, when I Google how to create a kernel density plot using Python, this thread still shows up. Today, a much easier way to do this is to use Seaborn, a package that provides many convenient plotting functions and good style management. All right, awesome, great. Wait, where was density mentioned? Density, I think density was mentioned here. Um, I think it was under probability distribution. No, it was here. Okay, density plot. That's where it came in. Okay, a probability distribution is a more specific concept that combines the idea of a distribution with the notion of probability. The idea of a distribution with the notion of probability. Hold on. I'm just gonna do something here because we just spawned a new doubt kind of spawned in my head. I'm learning about probability, or well, I'm learning about distributions in stats. You mentioned something about I'm just kind of planting fake context in the LLM's mind that yeah, okay, this is what it was. It's just gonna kind of run with it, which is kind of interesting. There's something this and a lot of other tricks. This is not really a trick. This is just something that I'm doing it and I hope that it works because I've seen it work in other cases. I'm not sure if it will actually work. If it works, great, awesome. Usually it works because you give it some fake context, then the LLM is just going to run with it. But yeah, I wanna. This is also one of the reasons why I want to go through that entire Kaggle course. I want to go through that course on stream. However, there are video segments of it where I believe they're mostly like discussing a bunch of things. I mean, the things are like related to this, and there's lots of very important information that you can get. But I think it's more of like a discussion kind of thing where they're giving a bunch. Though I don't know if there is like if there are like teaching. I think there are teaching segments in there as well. I'm going based off of what I saw in the first video. I could be wrong about that. My point is, in that 5 day course, there's video segments to watch, which are like live stream archives on the Kaggle YouTube channel, and there's also notebooks for each of those days, where you can, which go through various like practical examples of stuff that's being taught. I also need to look into any other additional papers that they might have published, any other additional course material that they might have published for us to read. But I want to go through that entire thing because I feel like that's going to be a good start for me because I've mentioned this before that I kind of wanted to get into doing LLM stuff, but I was going to approach it from like doing it from scratch completely. Um, but I feel like this is also a good approach. To be fair, this is also gonna, to a certain extent, help us approach it from scratch. But like, I don't know if it's gonna be completely from scratch. That being said, they are gonna teach us a bunch of like the foundational concepts and then build up from there. I'm pretty sure about that. I haven't even gone through the course, but I'm pretty sure that they're gonna that's how they're going to approach it. They're going to teach us a lot of the foundational concepts and then build up on that so we can create much more complex things using the various tools that are currently available. Where was I going with this? Why was I saying this? Oh yeah, I want to do the course on stream, but I need to see what portion of it is possible to do on stream and what portion I would much rather do off stream, because I'm not going to sit and watch videos on stream. Um, I I want to do stuff. I could read the notebooks on stream. So like they have Kaggle notebooks set up for each of these things, and I don't know, maybe some of the days might have multiple notebooks. I'm not sure, but they have Kaggle notebooks set up. I could go through those notebooks um, on stream. I'm gonna have to see how to go about doing that in a more in a safer manner because there are API keys involved in this. I'm gonna have to use Google AI Studio and Kaggle and probably a couple of other things where I have to be like logged in. And then, like I mentioned, the API key thing that's involved. So I need to make sure it's as secure as possible, or as less error prone as possible, I guess I should say. I'm not sure. But yeah, okay. Anyways, let's carry on with this. You mentioned something about, no, you know what? Let's make it better. We were having a conversation where you were teaching me about distributions in stats. You mentioned something about density. I would like to explore that concept more. Now let's see what the LLM gives us. Oh, this is another thing. PDF, probability density function. That's it. Yeah. So that's another thing that I learned that I need to look into. So this is like, it's a bunch of different terms that popped up, and as different terms popped up, I kind of I was kind of like just looking into each of those different terms. Um, and that's kind of why I wanted to continue doing it even on stream, because off stream also I'm just gonna carry on with this. So I was like, you know what, why not just do it on stream? Um, to understand the concept, oh, it did not get the. Okay, hold on. A probability density function is a function. Wait, okay, back up. Is this. Wait, you didn't mention a probability density function. Did I spell that right? No. Density function. You just mentioned density. Could you go more into detail with that? So, okay, the context thing that I was doing, it kind of worked, but kind of failed. I don't know. Wait, would probability density function give the same thing? Then there's also cumulative density function. To dive deeper in into the nope, nope, still not getting it. All right, let's try a different approach. Because I could be wrong. It could just be that like if I want to dive deeper into the concept of density, I do kind of have to go into probability density functions and cumulative density functions. Um, but I'm not sure yet. I just want to try and approach it from different angles and see if they all lead to the same thing, and then I'll just go with that path. So I'm learning about stats and data science. I'm trying to understand the concept of density and how to measure it. Let's see how okay, it's coming back to PDF and CDF. All right, so I guess that's density estimation. In practice, the true PDF may not be known. Okay, um, what is kernel density estimation? Okay, kernel density estimation is a non-parametric method used to estimate the probability density function of a random. Okay, so this goes back to PDF. This is used to estimate the PDF. What is the PDF supposed to be then? Okay, so to understand the concept of density in the context of stats and data science, you need to focus on the probability density function. So I've been trying to approach it from different angles, but it seems to be coming back to PDF. So I think my original approach previously, where I was trying to plant fake context, it did work. It's just that this is what it was leading to. And I thought it failed, but apparently it worked. Which I don't know why I'm surprised by that. I've done that multiple times in the past. I've done that with Gemini as well. Um, well, I did that with Gemini, I think back when we weren't able to save conversations, but like now you can save conversations. Now you can pin conversations and it so it maintains context for much longer, um, which is super useful. Like if we are looking at this Dude, I want to try building something like that. Something where I'm able to save the conversations or maintain memory or maintain context or something like that. Maintain context for longer. That's the key part. Not just maintaining memory and context in general, because it can do that for a certain amount of time, but then it just slowly starts to forget stuff. Um, yeah, okay. To understand the concept of density in the context of stats and data science, you need to focus on the probability density function, which is a fundamental concept for continuous random variables. Okay. Definition of PDF. A probability density function is a function that describes the probability distribution of a continuous random variable. Okay. It represents the likelihood of that variable taking on values within a specific range rather than at a single point. Okay, 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 wait, that's interesting. It represents the likelihood of the variable taking on values within a specific range. So it gives you the probability that the random variable is going to be within this range or that range or like, does it give it for multiple ranges? Or I think it has to be multiple ranges, right? Because like, how would you visualize if it was just one range? Or is it that in that range, depending on what kind of value you get, you can kind of like lean more towards a certain side? Okay, I guess I'll have to take like a practical example. So the PDF is denoted by so and so f of x, and it's defined such that the area under the curve of f of x between any 2 points a and b gives the probability that the random variable falls within that interval. Wait, let me read that again. The PDF is denoted by f of x and is defined such that the area under the curve of f of x, the area under the curve of f of x, um, the area under the curve of f of x between any 2 points a and b gives the probability that the random variable falls within that interval. Okay. Key properties of PDF. Non-negativity. The PDF is a non-negative. It is non-negative for all x. Okay. Total area. The total area under the curve of the PDF over the entire domain is equal to 1. This is expressed as so and so. Probability calculation. The probability that the random variable x falls within an interval a and b, or a to b, is given by the integral of the PDF over the interval so and so. Our relationship with CDF. The PDF is the derivative of the cumulative distribution function denoted as f of x. The CDF gives the probability that the random variable is less than or equal to a certain value. The CDF gives the probability that the random variable is less than or equal to a certain value. The derivative of the CDF at any point gives the rate at which this probability is changing, which is the density at that point. Graphical representation. The PDF is often graphically represented by a continuous curve. For example, the normal distribution or Gaussian distribution is a common PDF that resembles a bell-shaped curve. The area under this curve within a specified interval represents the probability of random variables falling within that interval. Okay, to understand PDF, to What? No, understanding the PDF is crucial for various statistical analyses such as central limit theorem, sampling distributions, confidence intervals. So, okay, sampling distributions. That was also something that I was supposed to be looking into. Did I note that down? Because there were a bunch of different topics that had popped up, and then I kind of like opened up more and more new tabs where I would start new conversations with another instance of llama. Um, hold on. Sampling distribution. Okay, density estimation. In practice, the true PDF may not be known, and density estimation techniques are used to construct an estimate. Okay, there's going to be an ad playing soon. I missed the ad timer. Whenever the ad starts, I'll let you guys know. So, um, where was I? And density estimation techniques are used to construct an estimate of the density function from observed data. This can be used. This can be done using parametric or non-parametric methods, depending on the assumptions made about the distributions of the data. By grasping these concepts, you will be better equipped to analyze and interpret continuous data in statistics and data science. Okay. I want to pick out something here. Um, Such that the area under the curve of so and so between so and so. Okay, so there's an ad playing right now. So I'll take a little hydration break and I'll see you guys in 30 seconds. All right, welcome back. So I was selecting this thing such that the area under the curve of so and so okay. What do you mean by this? I don't I don't understand this. What is going on with my spelling, dude? Actually, it's not the spelling. It's me mistyping. It's me hitting like two keys at my. Anyways, okay, whatever. I don't understand what this means. Okay, area under the curve. Oh God, is this going into calculus? Yep. Okay. To understand the concept of the area under the curve of a probability density function between 2 points, A and B, let's break it down step by step. What is a PDF? A PDF denoted by so and so is a function that describes the probability distribution of a continuous random variable and tells you the relative likelihood of the variable taking on certain values within a specified range. Okay. Okay. It gives you, wait, so it describes the probability distribution of a continuous random variable. It tells you the relative likelihood of the variable taking on values within a specified range. Sorry, zoned out. Okay. Um, it tells you the relative likelihood of the variable taking on values within a specified range. So how is it telling us this? Is it telling us this? Give me a sec. Yeah. How is it telling us this? Is it telling us this using a list of values or one value? Key properties of PDF. Okay, the total area under the curve of the PDF is equal to 1. This is expressed as so and so. Area under the curve. The area under the curve of the PDF between any 2 points A and B represents the probability that the random variable x falls within the interval so and so. Here's how it works. Integration. The probability is calculated by integrating the PDF over the interval. Mathematically, this is written as so and so. The integral gives us the area under the curve of so and so between so and so. Visual explanation. Imagine a graph where the x-axis represents the possible values of a random variable and the y-axis represents the probability density. Area calculation. If you shade the area under the curve between A and B, the size of this shaded area corresponds to the probability that falls within the interval AB. Give me a second. Okay. What was I what was I saying? Where was I? Uh yeah, okay. If you shade the area under the curve between A and B, the size of the shaded area corresponds to the probability that x falls within the interval AB. This is because the PDF is defined such that the area under its curve over any interval gives the probability of the variable falling within the interval. Okay, all right. Uh, okay. So does the PDF give us a list of values or a single value? How exactly does it, um, how should I phrase this? How exactly does it give us an estimation of the probability, or how exactly does it give us the probability of a random variable taking on a value within a specific range? Okay. The probability density function does not give you a list of values or a single probability value for a specific point. Instead, it provides a way to calculate the probability of a random variable falling within a specific range. I don't get it. Um, Probability calculation over an interval. To find the probability that a continuous random variable x falls within a specific interval, you integrate PDF over the interval. Yes, but I don't know how to integrate. And that goes into calculus, so I don't want to go into that just yet. For a continuous random variable, the probability of taking on a specific value x is 0, i.e. so and so for all. Instead, the PDF helps you calculate probabilities over intervals. Okay, okay, hold on. I need to approach this in a different way that doesn't involve me going into calculus. So let me explain it in this way. I don't know calculus. Okay. Um, I'm trying to learn about probability, distribution, and probability density function. How would I go about understanding them and using them without needing to use calculus? Keep in mind, I'm using Python and have access to various Python libraries. I'm adding this in there so it'll probably give me suggestions to use stuff like stats models or SciPy or scikit-learn or anything like that. There you go. There it is. Okay, all right. Let's take a look at the explanation first. Okay, to understand and work with probability distributions and probability density functions without needing to delve into calculus, you can focus on the conceptual aspects and utilize Python libraries that handle the mathematical complexities for you. Here's a step-by-step guide to help you get started. Okay, understanding probability distributions. Okay, so I know about this. Fortunately, I have understood the concept of discrete distributions and continuous. Oh, wait, no, I've understood the concept of discrete values and continuous values. I don't think I know about discrete distributions and continuous distributions. So I know the concept of discrete versus continuous, but I think a discrete distribution would involve something more. Okay, so these are distributions where before this, let's go back to what a distribution is. This is good. Okay, so what is a distribution and what is a probability distribution? Real quick, we're going to learn about this again, and then we're going to go back there. Okay, wait, let me hydrate, and then I'll read all of this stuff. Okay, um, where was I? Here. Okay, so a distribution in a broad sense refers to the way that the values of a variable are spread out or dispersed. This can be described in terms of the frequency or density of the values. For example, you might talk about the distribution of heights in a population. Back up. No, no, no. I need to understand this. A distribution in a broad sense refers to the way that the values of a variable are spread out or dispersed. So it's talking about the way that the values are spread out and dispersed, meaning that they could take on a specific shape or they could together have like that entire distribution could have a set of properties that makes it a certain type of distribution. But like, would we be calling the entire I guess I'm kind of confused about the vocabulary as well. Do we call a set of values a distribution, or is it more like we are saying that um, this set of values follows a certain distribution? Let's open up another tab. Okay, I'm learning about distributions and stats. I'm confused about the vocabulary. Are we saying that so both it's also possible that both of my assumptions are wrong and maybe it's something else, and if it is something else then Llama will tell me exactly what it is. All right. Are we saying that a set of values is considered a certain type of distribution based on certain attributes of the set, or are we saying that uh, a set of values follows a certain type of distribution based on certain attributes of the set? Okay. In the context of statistics, the terminology can sometimes be the terminology can sometimes seem interchangeable, but has a specific meaning. When we talk about a set of values in relation to a statistical distribution, we are typically saying that the set of values follows or conforms to a certain type of distribution. Here's why. A statistical distribution or probability distribution is a mathematical function that describes how values are distributed for a random variable. It defines the probabilities of different outcomes or the likelihood of the variable taking on specific values. Okay. Uh, when we say a set when we say a set of values quote unquote follows a certain type of distribution, example normal distribution, Poisson distribution, etc., it means that the observed data or the random variable's behavior can be described or approximate. Wait, back up. It means that the observed data or the random variable's behavior can be described or approximated by the characteristics of that specific distribution. For example, if a set of heights in a population follows a normal distribution, it means that the data points are distributed in a way that can be described by the normal distribution's characteristics, such as its mean, standard deviation, and the bell shaped curve. The attributes of a set, such as its mean, standard deviation, skewness, kurtosis, and kurtosis, help determine which type of distribution it follows. Okay, so generally we are saying that a set of values follows a certain type of distribution. We are not saying that uh, something is a distribution. We are saying that it follows a distribution. So the distribution is more of like a characteristic, I guess we can say. Is that the best word to use? It's more of a characteristic. So when we are saying that it follows a certain type, like it follows a certain type of behavior. Okay, let's carry on reading. Uh, where was I? Help determine which type of distribution it follows. For instance, a set of values with a symmetric bell-shaped curve and specific mean and standard deviation values would be said to follow a normal distribution. Sorry, zoned out. My God, my mind was just somewhere else for a couple of seconds. Um, yeah, zoned out. Um, where was I? Oh, yeah, okay. For instance, a set of values with so and so characteristics would be said to follow a normal distribution. So, to clarify, it is more accurate to say that a set of values follows a certain type of distribution based on the attributes of the set, rather than saying the set is a certain type of distribution. This distinction highlights that the distribution is a model or description of the data. Yep. Okay. That's a good way to put it. This is a description of the data rather than the data itself. Okay. Now, now we come back here. A distribution in a broad sense refers to the way that the values of a variable are spread. Now it's making more sense. Now it's making more sense. A distribution in a broad sense refers to the way that the values of a variable are spread out or dispersed. This can be described in terms of the frequency or density of the values. For example, you might talk about the distribution of heights in a population, which can be described by a histogram or a density plot showing how the heights are spread out. Okay. Probability distribution. A probability distribution is a more specific concept that combines the idea of a distribution with the notion of probability. It's a statistical function that describes the likelihood of obtaining all possible values that a random variable can take. The likelihood of obtaining all possible values that a random variable can take. Okay. Key characteristics, probability values. A probability distribution assigns a probability to each possible value or range of value. How does that work for continuous random variables? This could work for like discrete variables, right? But like, how does that work for continuous? How do you give all the possible all the possible values when the whole idea with continuous with a variable being continuous is that it can be anything. It can be even like a fraction of something. So like you don't know what exactly the value could be. These probabilities are expressed as numbers between 0 and 1, where 0 indicates an impossible event and 1 indicates a certain event. Okay, so real quick, if we are thinking about a normal distribution, are we saying that considering the bell-shaped curve, the outer values are more impossible and the central values are much more possible? There's a much higher probability of them um, being chosen. I was for a second there I wasn't sure what words to use. There's a higher probability of them being chosen. Okay, sum of probabilities. The sum of all probabilities for all possible values must be equal to 1. This ensures, also it's kind of like a softmax function. This ensures that the distribution is valid and accounts for all possible outcomes. Okay, all right. Types of probability distributions can, no, types. Probability distributions can be either discrete or continuous. Discrete probability distribution. This describes scenarios where the random variable can take on a countable number of distinct values. Examples include the binomial distribution and the Poisson distribution. Continuous probability distribution. Uh, this describes scenarios where the random variable can take on any value within a given range. Oh, that's how it does it for continuous variables. It gives you the probability of like within a given range. Examples include the normal distribution or wait, or other continuous distributions like the Birnbaum Saunders distribution. I'm gonna have to look into that later. Okay, that was gonna be my next question. Representation. How are you representing these values? Probability distributions can be represented in various forms. Probability mass function for discrete values, for discrete variables, which assigns probabilities to specific values, and probability density function for continuous variables, which describes the probability of the variable falling within a given range by the area under the curve. I'm not getting that part. I'm having trouble understanding that part. Wait, okay, so we learned about distributions, right? And now we are coming to discrete distributions and continuous distributions. Then key concepts without calculus. Oh yeah, I forgot we were doing this. Okay, great, cool. So um it's all kind of coming together now, I guess. Okay, um where should I ask the next question? I think here. Okay, so I don't understand how a probability density function gives sorry, zoned out. I don't understand how a probability density function gives um what was I where was I going with this? Oh, yeah, how it gives us the probability of a random variable being a continuous random variable um, being within a certain range. Doesn't it have to give us a group of values representing the probabilities? How are we quantifying this? Okay. Um, oh God, it's coming back to this again. All right, to understand how a probability density function, yeah, so it quantifies it using that area, and then that area is used with something else. Is a function that describes the relative likelihood of different values of a continuous random variable x. Wait, what? That describes the relative likelihood of different values of a continuous random variable x. It is not a probability itself, but rather a density that, when integrated over a range, gives the probability of the variable falling within that range. Okay, wait. Okay, all right. So I need to find a way to do all of this using either stats models or SciPy or scikit-learn. So we are gonna go back to this, which I'm sure is now gonna show us how to do what I was trying to do. Give me a second. Let me hydrate and then I'll carry on reading. Okay, all right. So discrete versus continuous distributions. Just a second. Okay. Yeah. Discrete versus continuous distributions. So discrete distributions are distributions where the random variable can take on distinct countable values. Examples include the binomial distribution, the Poisson distribution, and discrete normal what? No, the and discrete uniform distribution. I need to look into what that is. You can work with these using probability mass functions. Okay. Continuous distributions. These are distributions where the random variable can take on any value within a given range. Examples include the normal distribution, uniform distribution, and exponential distribution. Okay. These are described using probability density functions. Okay, so for discrete distributions, we use probability mass functions, and for continuous distributions, we use probability density functions. You can work with these using these functions. Okay, all right. Key concepts without calculus. So for cumulative distribution functions, CDF denoted by so and so takes on a value less than or equal to x. For discrete distributions, it is the sum of the probabilities up to x. And for continuous distributions, it's the integral of the PDF up to x. But you can use pre-computed tables or libraries to avoid calculus. Okay. Um, Probability density function. While the PDF is technically defined using calculus, you can still, no, you can think of it as a function that describes the relative likelihood of different values. You don't need to integrate it yourself. Instead, use libraries to generate and manipulate PDFs. All right, let's take a look at examples using SciPy and stats models. These libraries provide functions to provide what? These libraries provide functions to work with. Let me hold on, dude. These libraries provide functions to work with various probability distributions without needing to perform the underlying calculus. So we have scipy.stats. which includes functions for many common distributions. For example, you can use scipy.stats.norm for the normal distribution and .uniform for the uniform distribution, and so on. You know what? As it's telling us this, we can also look into it. Um, so here it's given more detail about SciPy, even though stats models has like a lot more, at least from what from the bit of research that I've done, it seems like stats models has a lot more advanced stats related functions and um, tools and stuff. But we are still going to look into the SciPy thing because currently, specifically for what we are trying to do, um, the thing seems to be in SciPy. Okay, so we are here. Let's just zoom in a bit so we can read. Okay, all right. This module contains a large number of probability distributions, summary and frequency statistics. Summary and frequency statistics, correlation functions, I could use that, and statistical tests, masked statistics, kernel density estimation, quasi Monte Carlo functionality. I have no idea what that means, but okay, and more. Statistics is a very large area. You know what? I might be wrong. So I was going based off of what other people have said about SciPy's stats capabilities. Not that SciPy is lacking in stats capabilities, just that apparently stats models is a lot better, or in this, or it has a lot more functionality. I should put it that way. A bunch of people were saying that. I think even the LLMs were saying that. Either way, okay, whatever. I'm gonna be exploring both of them either way, because I'm looking into doing a bunch of stats related stuff. So I'm gonna need to explore both of these if to see which one has what features I'm looking for in a specific scenario. Statistics is a very large area, and there are topics that are out of scope for SciPy and are covered by other packages. Some of the most important ones are, there you go. We have stats models. Okay. And Seaborn is also mentioned. Okay, probability distributions. So we have continuous and discrete. Okay. We are looking for continuous right now. So under continuous distributions, let's take a look at norm. There's a bunch of different types of distributions, but we are looking for norms specifically. Man, there's so many of these. Holy shit, there's like so much to explore here. NO, norm. A normal continuous random variable. Okay. A normal continuous random variable. The location lock keyword specifies the mean. The scale keyword specifies the standard deviation. Wait, the mean supposed to be uh isn't the mean supposed to be 1 and the standard deviation 0? Like isn't that a normal distribution? Or did I get that wrong? I'm gonna have to look into it just to kind of refresh my. Oh, so okay, mean is set to 0. Oh, the mean is supposed to be 0 and the standard deviation is supposed to be 1. I think that's it. Isn't it? I think so. I think so. I'm not sure. The norm object inherits from it a collection of generic methods and completes them with details specific for this particular distribution. Probability density function, the log, random variates. I think that's what I'm looking for. Cumulative distribution function. Okay. You know what? Let's test it out and see what pops up. Give me a second. Okay. So, so there's a bunch of functions here, but I think the one I'm specifically interested in, why is there a fit method here? Parameter estimates for generic data. Okay, all right. Um, Notes, the probability density function for norm is so and so. For real number x, the probability density above is defined in the standardized form. To shift and or scale the distribution, use the lock and scale parameters. Specifically, norm.pdf is identically equivalent to norm.pdf. Wait, what? Oh, okay. Okay. With y equals so and so. Note that shifting the location of a distribution does not make it a non-central distribution. Non-central generalizations of some distributions are available in separate classes. Okay, we have an example here. Calculate the first 4 moments. You know what? I need to ask this question here, maybe, or which tab were we in? I think this was the one. Yeah. Okay. Um, I'm looking into scipy.stats.norm docs. I'm wondering what moments are. In the context of statistics and scipy.stats module, moments are quantitative measures that describe the shape and characteristics of a distribution or a set of data. Oh, so like mean, standard deviation, and stuff like that. How is the symmetry? How is the symmetry quantified? I guess I should say. Oh, I also need to look into skewness. I haven't had the chance to look into skewness yet. Okay, here are the key points about moments. Definition: a moment is a measure of the distribution of a set of values. Wait, what? A moment is a measure of the distribution of a set of values. It is defined as the expected value of the power of the difference between the values and a central point using the mean. I did not understand that. Um, yeah, I didn't get that. Okay, raw moments. These are calculated about the origin, 0. However, in most statistical contexts, moments are calculated about the mean. Central moments. These are calculated about the mean of the distribution. The most common central moments are first central, second central, third, and fourth. The first central moment, this is always 0 because it is the mean of the deviations from the mean. It's the mean of the deviations from the mean. Okay. Okay. Wait, I'm trying to remember mean, standard deviation, and variance because they're all kind of like tied in together. So you have the mean, which is the average. That's fine. I think standard deviation was the squared difference, or it was the mean of the squared difference. No, yeah, I think it was the mean of the squared difference. Let me just real quick do something here. Okay, we're gonna run this. So the notebook starts, and then I'm gonna create a new code cell here. A equals np dot array 1 2 3. Oh, what just happened? Oh God, something just. Let's not do that. Okay, all right. Um. Okay, a dot mean. So let's print out a dot mean. All right, that's our average. Then let's print out the standard deviation. That's that. So standard deviation is one value. Standard deviation is the squared difference from the mean. Is that right? No, I think it's the mean of the squared difference. Yeah, I think it's the mean of the squared difference. Wouldn't that make sense? Because let's try this. Let's say squared difference, right? The mean is that. Okay, let's do 1 minus 2 plus, wait, we're trying to get the mean, right? Yeah, okay. Mean of the squared difference. 2 minus 2 plus 3 minus 2, right? And then we divide this by 3, right? Did I get that right? Almost. Okay. Yeah, that didn't work. Should I make these all decimals? Nope. Still didn't work. What am I actually, maybe I should look up the way to calculate the standard deviation. I'm trying to remember. Okay, hold on. Instead of just trying to remember this and doing a horrible job, let me just look it up. Okay. So standard deviation is a measure of the is a measure of the amount of variation of the values of a variable about its mean. A low standard deviation indicates that the values tend to be closer to them. So are we subtracting it from the mean? That's what I did here, right? Why did the result come out to 0? So this would give us -1. -1 plus 0 is -1. Oh, and then -1 plus 1 is 0, and then 0 divided by 0 divided by 3 is, well, this. Right, that's why it didn't work. So I'm missing something here. Um, okay, these 8 data points have the mean so and so. Okay, so you divide it by that and you get that. Okay, first calculate the deviations of each point. Oh, is it because I didn't? Is it because I forgot to square? I said it's squared deviations, right? Or, well, the squared differences. The squared differences. Let me just check this real quick. Square root. Okay, so let's try this. Actually, let's just confirm. Let's just confirm that this works. Um, right. So square root should be 3, and it's 3. Okay, cool. So we're gonna run this thing again. It is the squared. It's the mean of the squared differences. Is it? Is it the mean of the squared differences? I think so. I think so. Okay. Uh, Square root. Okay. Square root. Okay. Square root. Okay. We have a problem here. Oh, it says not a number. Oh God, what just happened? Okay. Yeah. Uh, what if I made this an absolute value, since I know this is going to be... All right. That's still wrong. Okay. Let's see. The variance is the mean of these values, and the population standard deviation is equal to the square root of the variance. Oh, that's how the variance comes in. The variance is the mean of these values. The variance is the mean of the squared differences. So let me just confirm. How do I get variance? Compute the variance along the specified axis. Okay. Okay. All right. So back up. So I don't think I need this right now. Okay. All right. So we don't need square. Why was I doing square root? I was supposed to be doing square. Yeah, why was I doing square root? Dude, I just realized that. Why was I doing square root? So, if we take the square and then divide it by, so if we take the mean of the square, uh, if we take the mean of the squared differences from the mean, then hold on. Okay, let's do that and do that. I could use arithmetic precedence here, but I just want to do it this way. Okay, let's see if that helps. So that should be our variance, right? Let's try printing out the variance of A. That is our variance. Okay, that is our variance. And then The population standard deviation is equal to the square root of the variance. How do we get 0.8? By taking the square root of 0.6. Okay, so let's say A variance equals this, right? And then let's take the square root of, well, fuck me. Okay. Uh, right. So I guess I'm remembering now. So okay, earlier when I was saying that the three are connected in some way, what I was thinking was like, okay, we're able to calculate the mean and then the standard deviation, and then out of that we're able to calculate the variance. But it's kind of the other way around. It's like we calculate the mean and then we calculate the variance using the mean, and then using the variance we can calculate the standard deviation, which is basically just a square root. Right. How did I get to this? I think I was looking into moments. Yeah, I think that's how I got to it. Now, yeah, I was confused about moments being mentioned here. Calculate the first four moments. Norm.stats, moments, so and so. Okay. Display the probability density function. Alternatively, the distribution object can be called as a function to fix the shape, location, and scale parameters. This returns a frozen RV object holding the given parameters fixed. Okay, all right. And finally, we are able to generate random numbers. Okay, all right. Um, right. So this is plotting that, and then how is it plotting this thing? Density equals true. Is that how it's plotting it? Also, what is this? Norm inverted? A normal inverse Gaussian continuous random variable. What does that look like when it's visualized? Oh, that's interesting. Uh, as an instance of the continuous class. Okay, all right. You know what? We'll look into this later. I just hit something which caused the page to refresh, I think. I'm not sure. Okay. All right. You know what? There's going to be an ad playing in the next minute and a half, I guess, and I need to take a short break for a couple of minutes. So I'm just going to switch to the BRB screen, and then pretty soon the ad will be starting. And yeah, okay, cool. So I'll be back. I'll be back in a couple of minutes. All right. Okay. So we are back. Also, welcome back from the ads. Um, right. So I've been trying to understand moments. I haven't really, I haven't really understood. Hold on. A moment is a measure of the distribution of a set of values. It is defined as the expected value. It is defined as the expected value of the power of the difference. See, this is where it gets. It is defined as the expected value of the power of the difference between the values and a central point, usually the mean. Okay, types of moments. Raw moments. These are calculated about the origin. However, in most statistical contexts, moments are calculated about the mean. Sorry, zoned out. Okay, so okay, there's 3 and 5 mentioned here. What is 3 and 5? What is it? Okay, hold on. In the scipy.stats module, you can calculate moments using the moment function or through the methods provided by distribution objects like so and so. Okay. There's what was it? Norm.moments, I think. Where is that example? Stats.norm. Okay, okay. I think it was in the example. Norm.stats. Oh, so it's stats.norm.stats. Okay. All right. Let's do that, I guess. So import, what was it? scipy.stats.norm as norm. Actually, I don't think I need to do that, right? This did not work. What's the issue? scipy.stats.norm, right? No module named scipy.stats. Is SciPy not a thing here? No, I'm pretty sure SciPy is installed. SciPy is installed. Okay. Then stats. Norm is not a module. Okay. 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 As norm. Norm is not a module. Okay. All right. Norm is not a module, so I need to import, right. So from scipy.stats, import norm. There we go. That works. Great. Okay. Mean. What all was there? Mean variation, skew, and kurtosis. Mean variation, skew, and kurtosis equals norm dot stats. Let's see what IntelliSense shows here. Okay, IntelliSense is not cooperating right now. There it is. Some statistics of the given RV. RV is random variable. Okay. arg1 to so and so, so and so, so and so. Okay. For the distribution, C doc string for, okay, scale moments. Optional composed of the letters M, V, S, K. Okay. Defining which moments to compute. M, mean, V, variance. Okay, yeah, I got that. Dude, I need to look into skew and kurtosis. I need to, hold on. Does the word skew pop up anywhere here? Skewness. Skewness and kurtosis. All right. Um, in probability theory and statistics, skewness is a measure of the asymmetry of the probability distribution of a real valued random variable about its mean. The asymmetry of the probability distribution. So if we are looking at a normal distribution, or we are trying to see, I guess if we are trying to see how close to a normal distribution a certain set's distribution is, I guess skewness could be one of the measures of that, because a normal distribution is categorized by symmetry around the mean, or, well, symmetry on both sides, but I think it's around the mean and the mean is the center. I think so. I'm going to have to visualize one of these. I think the mean is the center. I think so. Because the mean is 0, isn't it? Yeah, that's a normal distribution. Mean is 0, standard deviation is 1. Um, the skewness value can be positive, 0, negative, or undefined. For a unimodal distribution, a distribution with a single peak, negative skew commonly indicates that the tail is on the left side of the distribution, and positive indicates that the tail is on the right side. The tail, oh, the tail as in the top end? Oh, that would make sense. Actually, yeah, that would make sense. Because if we are talking about a distribution with a single peak, isn't normal distribution also a distribution with a single peak? And so then by that logic, the quote unquote tail would be the bell curve, like the thing. And that's usually in the center for a normal distribution. But if it's skewed, we're going to have the tail on the left or the right side. This is just my interpretation of this. I'm not sure how accurate it is, but I'm I guess I'll have to run some tests to confirm this. For example, a 0 value in skewness means that the tail on both sides of the mean, the tails on both sides of the mean balance out overall. This is the case for a symmetric distribution, but can also be true for an asymmetric distribution, where one tail is long and thin, and the other tail is short but fat. Okay, all right. The skewness is not directly related to the relationship between the mean and the medium. Okay, so I'm realizing now that we've kind of branched out quite a bit. And what we were initially supposed to be looking at, we are not looking at that anymore. Either way, okay. What is kurtosis? Kurtosis refers to the degree of tailedness in the probability distribution of a real valued random variable. Similar to skewness, kurtosis provides insight into specific characteristics of a distribution. Okay. Various methods exist for quantifying kurtosis in theoretical distributions, and corresponding techniques allow estimation based on sample data from a population. It's important to note that different measures of kurtosis can yield different interpretations, can yield varying interpretations. The standard measure of a distribution's kurtosis, originating from Carl Pearson, where have I heard this name? It's Pearson something something. Yeah, yeah. There was a thing. Pearson something something. What it was something to do. There's some kind of there's like algorithms under this person's name, or maybe it wasn't Carl Pearson. Maybe it was some other Pearson. I'm not sure. Um, Statistics. Okay, there it is. Yeah, Pearson's correlation coefficient. That's what I was remembering. Yep. Pearson correlation coefficient. I was looking into this as well. This was like on a separate thing. Correlation coefficient, covariance matrices, and stuff like that. I was looking at that on like on a different system, which I need to get back to that as well, because a lot of these things, these are kind of like the primer for um they're kind of the primer for being able to study data, or rather I think that these are kind of the primer, or this is like some very basic knowledge that I'm going to need to have if I'm going to be exploring um, data and trying to find patterns in data. Which, by the way, yesterday I found out that apparently what I've been trying to get into is data mining. Like, I knew about data mining way back when, but I had no idea. I guess probably because I didn't fully understand the meaning of data mining, because in my head, data mining was more about data collection, not about trying to identify patterns in data. So I don't know if I had the wrong idea of it, or just an incomplete definition of it. But yeah, apparently, what I'm interested in is data mining, trying to find patterns in data and transforming the data into different types, so that I can find patterns in them. Basically, it all comes down to finding patterns in data. And for all of that stuff, uh, I need I need to know a bunch of this, what I consider basic stuff, basic stats stuff. So I'm trying to cover all of these things, and then gradually I'm gonna go into more complex stuff. And the more complex stuff is fortunately already covered in scikit-learn, so I'm not gonna have to worry too much about understanding the math behind them. I just need to understand how the algorithms work and what exactly they're doing. Give me a second. Okay. All right. Kurtosis. It's a measure of the tailedness. So how, for lack of a better term, pointy the tail is. This number is related to the tails of the distribution, not its peak. Wait, the standard measure of a distribution's kurtosis, originating from Carl Pearson, is a scaled version of the fourth moment of a distribution. Of the distribution. This number is related to the tails of the distribution, not its peak. Oh, so it's probably not how pointy. Well, it could still be how pointy it is without worrying about how high it is, right? Hence, the sometimes seen characterization of kurtosis as peakness is incorrect. For this measure, higher kurtosis corresponds to greater extremity of deviations or outliers, and not the, my God, will you chill out? Holy shit. Yeah, and not the configuration of the data near the mean. Um, Encoders, hello, hello, welcome to the stream. Thank you for the raid. Holy shit. Thank you for the raid. Actually, encoders and raiders, welcome to the stream. Hello, hello. Let me give you a shout out real quick. Thank you for the raid. I appreciate it. Just a second. Oh God, my keyboard is not cooperating with me. Is that? Yeah, there it is. So you guys should go check out encoders. Yeah. Okay. There. I was giving a second shout out through the shout out command thing. But yeah, hello, hello. Hello encoders. Welcome raiders. Thank you so much for the raid. We are studying a bunch of different stats related things today because there's a bunch of stuff that I need to learn about. So I was supposed to be learning about probability distribution. How are you doing? I'm doing good. I'm doing great. I'm learning stuff. I hope you're doing well. I don't know if I said this. I hope your stream went well. I don't think I said it. I hope your stream was good. Let me know what you guys were up to today. Are you studying distributions? It looked interesting and related to our topics. We are, yes, we are studying about distributions. So I was kind of trying to understand the idea behind distributions, and I understood that. Then I was looking at probability distributions and the different types of probability distributions, and also how the probability distribution gets quantified, or how it gets displayed. Like how do we show that this is the distribution? I was trying to get an understanding of that, and I didn't want to go deep into. Also, Jara, thank you for the follow. I didn't say that previously. I saw the notification, but I forgot to say it. Thank you for the follow. So what was I saying? Shit. What was I saying? Um yeah, so I didn't want to go deep into calculus in order to study distributions. Also because, you know, well, mostly because I don't know too much about calculus, but also because there are functions available from various Python libraries that will allow me to do that. So I was trying to get an understanding of the distributions first and how to quantify them. And then I was going to try and do that through various libraries like SciPy and stats models. And if scikit-learn was necessary, then also scikit-learn. And this was a small detour that I was taking because I suddenly got distracted with the concept of moments because we were looking into SciPy. We were looking into generating a normal distribution or a normal continuous random variable uh, using SciPy. And I kind of got hung up on moments because I don't know what moments are. So I tried asking Llama, and Llama gave me this answer. Wait, did I? Um, I think I asked it again later on. So it gave me this definition. A moment is the measure. A moment is a measure of the distribution of a set of values. It is defined as the expected value of the power of the and this is where I started to get lost. It is defined as the expected value of the power of the difference between the values and a central point, usually the mean. Now, I don't think I need to calculate moments myself, but I do want to get an understanding of what moments are because there's this thing of first, second, third, and fourth moment, and that is being calculated here in the form of mean, variance, skew, and or skewness and kurtosis. By the way, I don't think I printed these out. Yeah, let's try that. So moments equals what was it? Mean, variance, and this. Was it SK or KS? SK, okay. And then let's try printing each of these out. Mean, variance, skew, and kurtosis. That did not work. Oh, is it stats? Oh, yeah, it's stats. Okay. Uh, okay. So mean is 0, variance is 1, skewness is also I think 0, and kurtosis is also. I'm not sure where it's picking up these values from. I need to look into that. Yeah, I need to check where it's picking up. Like what exactly is it getting the mean of? Because mean is 0. And in what situations would you get a variance of 1? So let's try this. Let's say array. I don't think I need to calculate the thing manually. Oh, actually, I think variance 1 would also be in situations where like I was about to use 0, but I think in any situations in any situ though would variance be 0 then? Not 1. Let's hold on. Let's see. A dot is it a method? Yeah, it's a method. Right. That doesn't work. What if we do this? That doesn't work either. So how is it getting a variance of 1? I need to let me look at how do I get to what was it? Norm.stats, I think. Standard deviation of the district. Oh, it's the mean and the variance of it's the mean and the variance of the normal distribution. And the normal distribution is the bell curve type thing. As in it has a specific shape. And in a normal distribution, the mean is supposed to be 0, right? The standard deviation is supposed to be 1. Um, the standard deviation is the square root of the variance. So, I mean, that would still be, yeah, that would still be 1. So that's why variance is 1 as well. And there's no skewness in it because it's central. I'm not sure about kurtosis. I haven't fully understood that concept yet, so I'm gonna have, as far as I can tell, it's more about how wide the tail is. And skewness is more about where the tail is, on which side. All right, so given all this, wait, why exactly was it doing this? Why exactly was it calculating the first four moments? So we calculated, then we display the probability density function. Alternatively, the distribution object can be called as so-and-so. Okay, all right. What if I don't want the PDF? What if I just want, do I still need to generate the density function? This is just to, this is just to display it, right? So I think everything is calculated, is being calculated in the background anyways. So what if I just try to do something like this? So let's generate a set of random numbers and then try plotting it on a histogram. So we'll do this dot histogram. Let's do B. Oh, actually, I could do A, right? So A could be, what was the thing? Norm.rvs, I think. Do I need to initialize something or instantiate something? Okay, norm. There was an RVS function for generating random variables. Is that what's being used here? I think so. Norm.rvs. I don't think I need to initialize anything, so I guess we can just do this. We can try experimenting with different means and different variances. I think what were the different arguments that it takes? It had different arguments here. Location and scale. Yeah. And because the default is set to 0 for location, I'm assuming that's the mean. I think it also mentioned somewhere here that it's the mean. Oh, yeah, there you go. Keyword specifies the mean, and then the scale keyword specifies the standard deviation. All right. So for now, let's just go with this, and let's generate about 3,000 samples. And then what were, I forgot what the arguments for this were. Okay, so it takes X and bins, range, don't need to worry about that. Density, I guess we can set that to true. Okay, so we pass in A. Let's do about 50 bins. Density equals true. Okay. There is an issue with, oh, bins. All right. Okay, cool. So this does a similar thing. What if, so I have a lot of experimentation to do around this because I find the concept of normal distributions very interesting for some reason. Like there's a lot to study around this, and I want to see what kinds of data sets or what kinds of data ends up following a normal distribution. There are a bunch of data sets provided by scikit-learn that I wanna try and run these tests on. Not just normal distribution tests, but other, actually a bunch of other tests. Because like I was looking into, hold on, I was looking into this. these two pages, I need to explore them more. Also clustering, but yeah, Gaussian mixture models and manifold learning. There's a bunch of interesting stuff in here that I wanna explore. Okay, all right. Where was I? Because I feel like I've branched out quite a bit. So normal distribution, I generated a normal distribution using this. Dude, okay, what happens if I change the mean? Let's see if it kind of if it affects things. Also, let's maybe generate um a much bigger data set. All right, okay, cool. What was I gonna do? I forgot what I was about to do. Holy shit. I forgot I forgot what I was about. Oh, yeah. I was about to change this. So let's try changing the location. So the mean is supposed to be 0. What if we change the mean to negative 0.5? Just throwing something out there. That seems to have shifted things a little bit, even though it doesn't show up here. I have a way to make it show. The range. We are able to specify the range. What is the range expecting? A tuple? Wait, let's do plt.hist. Um, I cannot read that. That is that is off the screen. I think I opened up Matplotlib's thing here for histogram. Great. Okay. So we have, where's the function? I'm looking for the function. I think this will be the same as the axis. I think this will be the same as the PLT version, right? Okay, let's go to this. Um, where did this bring me? Okay, let's just look up hist. PyPlot hist. That's what I'm looking for. Okay. Uses NumPy to create histogram. Okay, all right, cool. Range. What is expected in range? A tuple or none. And that's going to be, all right, okay, cool. So we set the range to be negative negative 5.0 and positive 5.0. Just so we have sort of a central location, just so things are centered. And so if something is off the center, which it seems like it here, I think that's because I set it to negative 0.5. So, so the mean controls where the distribution is going to be, or where I guess the center of the distribution is going to be, where the peak of the distribution is going to be. So if I set it to something like this, it's going to be like way off to the left. Interesting. What else was there? Standard deviation. Okay, let's try changing that. So let's set this to 0. And then what was the other thing? Shape. I think. Scale. It's called scale. So let's try setting the standard. Is the standard deviation supposed to be between 0 and 1? I don't remember. What if we try setting it to 2? Oh, that's interesting. Okay, what if we set it to 0.5? Look at that, dude. So you're essentially able to tune or tweak values to control the shape of this normal distribution. All right, we were looking at, I think we were here, right? We were trying to look into ways to deal with distributions, normal or otherwise, without going into calculus and using Python libraries. So it suggested SciPy and stats models. I should look into stats models documentation as well. Did I open stats models somewhere here? Just a second. Okay. So where's the documentation? Here. I think it's under. Should I go to API reference? I guess. Yeah, because there's a. I think there's a stats model dot. Was it under API? No, you know what? Let's just search. Um, what is it? Normal? Okay, let me try searching elsewhere. Normal distribution. It is under something called distributions. All right, so count distributions. Okay, okay. Distribution extras. Okay, I'm gonna have to look. Wait, distribution non-monotonic, based on a non-monotonic something. Okay, I'm not sure what that is. Okay, okay, okay. Not sure which one I'm looking. Oh, maybe I should look for Gaussian. What's copula? Okay, let's try opening this up. Oh, you know what? Let's try asking. Dude, we were supposed to be learning about moments. Oh, hold on. This is interesting. Central tendency, which is the mean, spread or dispersion, which is the standard deviation, basically, isn't it? Or, well, variance. Uh, Asymmetry, and then tailness. Okay, so this is sort of a standard thing. Moments provide insights into the shape and spread of the data. Dude, okay, what if okay, is there a way? So I'm giving it these values, right? Is there a way to, let's say I want to instantiate the thing like this. Is that a possibility? Because what I want to do, also, what does this return? Oh, this returns basically a list. Though if I, yeah, okay, how would I get the skewedness and the kurtosis of this? Would I need to calculate that myself? Because if I try to use, so let's try running this again and then do this again. Oh, I could have just copied both those. Never mind. Uh, yeah, it's still not changed. Though, wait, norm.stats, doesn't this also take some arguments? Where was it? Yeah, the stats, I think the stats function does also take some arguments. So if I passed, let's try passing these values in here and see what it gives us. And then we do moments equals, oh, actually, wait, 0.5, bring this here. Now, let's copy this. I don't think I need to copy this. There's already a copy up there. Okay, and then print this out. So we have a variance of 0.25, but skewness and kurtosis is showing as 0. I'm not sure if it's giving based on this distribution, if it's giving its values based on this distribution or not. Let's try setting, okay, 2. All right, so the variance does, oh, these are different. I just realized that. So let's do this just so I can have it standard across all of them. Let's do that and that. Uh, okay. Right. That's much better. All right, what if I offset this by negative 0.5? Okay, so that's not changing the skewness, even though it is a bit skewed. So I must be doing something wrong here. Or maybe my understanding of what norm.stats is doing, uh, maybe my understanding is off. So this is our normal distribution. It's offset by a bit. Let's try giving it some crazy values. Let's say, I don't know, 5.5. This is going to be off. It's going to be outside the range. These are still not changing, which is interesting. Let's try asking when I use norm.stats in what is it in SciPy? In SciPy, and I no, regardless of what values I pass to lock and scale, the skew and curt return are always 0. Explain this. You know, there's something else that I didn't take into account. Uh, Real quick, before I read this, something else I didn't take into account. Let's say we do this, right? We are shifting this, but the shape doesn't change. It just gets offset. So I don't think there is any skewness to it. I think that's why the value is 0. Though that doesn't explain why kurtosis is 0. But to be fair, I also don't fully understand the concept of kurtosis yet, so I can't say for sure what the situation is there. Um, just a second. Give me a little bit. Okay. Um, right. I was looking into something called copula or copula. Uh, Copula is a word or a phrase that links the subject of a sentence to a subject complement. Right, that's not the answer I was looking for. Let's try. Wait, before that, let's also come here. I think I kind of got the answer for skewness. Why skewness is 0? It's because the thing is not skewed, which makes me wonder, what if we want to skew it? Is that a possibility? Because like if we do skew it, it's not going to be a normal distribution, but are we still able to skew it? Right? Because we have location, we have scale, we have size. How do we skew this? Stats, so and so. Okay. All right. Mean of the distribution, variance, standard deviation, median. Okay, all right. It's giving us, okay, so this is great. I'm starting to understand it slowly. I'm starting to understand the various functions that are given here. Just a second. Oh God, what just happened? Yeah, just a second. Yeah, I'm starting to understand the various functions that are given here. These are great helper functions, but like they all mention like location and scale. So I think it's more that you are able to give it a certain type of mean and variance, and it will then calculate the thing based on that. I'm curious as to what kind of mean you would get here, because location is the mean, scale is the variance. So like, wait, let's test that out. So let's do norm.stats. Uh, no, it's not norm.stats, is it? It's norm.variance for, wait, it was giving some, it's a location, optional location parameter, scale, optional scale parameter, variance of the distribution. So if we give this and this, then variance should just be one, right? Then like, what's the point? Because then mean is also the same thing. Oh, what if, hold on. What if I try changing the values to something else? Maybe then it makes a difference. So what if I do that? Yeah, then it makes, okay. Now it makes a difference. Right, right. Okay, so there is a need for some reason my mind was stuck in like that 0 to 1 range, and I was like, okay, how is this? Why is this necessary? But yeah, it is. It's necessary. Um, right. Where was I with this? I was looking into the skewedness thing, but also, just real quick. Give me a second. Doing something. Okay. So what was I? Yeah, I was I was reading this. I keep forgetting. So the normal distribution, also known as the Gaussian distribution or bell curve, has specific properties that define its shape. Two of these properties are Okay. Two of these properties are skewness and kurtosis. Skewness, for skewness, the normal distribution is symmetric around its mean, which means the skewness is always zero. Right. So it's what I thought. Skewness measures the asymmetry of the distribution, and since the normal distribution is it's perfectly symmetric, its skewness is zero. And then kurtosis. In Fisher's definition, the excess kurtosis of a normal distribution is zero. This means that when you calculate kurtosis using Fisher's definition, which is the default in so and so, and and implicitly used in so and so, the result for a normal distribution is always zero. Kurtosis measures the tailedness or peakness of the distribution relative to a normal distribution, and a normal distribution serves as a reference point with zero excess kurtosis. Let's read that last thing again. Kurtosis measures the tailedness of the distribution relative to a normal distribution. Okay. And a normal distribution serves as a reference point with zero excess kurtosis. Okay, this adjusts the location, which is the mean, and this adjusts the scale, the standard deviation of the normal distribution, respectively. However, these parameters do not affect the shape of the distribution in terms of skewness and kurtosis. You know what? Let's try asking Llama. Help me understand kurtosis. Okay. Uh, Kurtosis is a statistical measure that describes the shape of a distribution, particularly focusing on the tailness or the presence of outliers in the data. Here are the key points to help you understand kurtosis. Kurtosis measures the degree to which a distribution is more or less tailed compared to a normal distribution. What does tailed mean here? It indicates how much data resides in the tails of the distribution, which are the regions farthest from the mean. The farthest from the mean, for some reason, I kept thinking of like the center, but like, okay, if we are saying the farthest from the mean, that's basically like the far ends, right? So that would be, let's center this. So like these would be the far ends, right? Okay, so it measures which regions are the farthest away from the mean. It indicates how much data resides in the tails of the distribution. Types of kurtosis. There are three main categories of kurtosis: uh, mesokurtic, platykurtic, and leptokurtic. Okay, mesokurtic is a type of distribution that has a kurtosis similar to that of a normal distribution. It represents a moderate level of risk and tail heaviness, similar to the normal distribution. Platykurtic. This distribution has a lower kurtosis. Hold on. I need to understand what tailness. So kurtosis primarily measures the weight of the tails relative to the rest of the distribution. Higher kurtosis indicates more data in the tails. But if normal distributions trail off towards zero, the tails don't have any weight, right? Like, am I missing something there? So like, okay, how do we calculate kurtosis in general? Um, okay, does NumPy have a kurtosis option? Calculating kurtosis from a NumPy array. Okay, SciPy has a stats thing. SciPy.stats kurtosis. NumPy is restricted to fairly basic array operations. Okay, that's fine. Stats SciPy.stats import sensor. Okay, cool. Let's do it. Actually, hold on. We're gonna we're gonna pause here. Okay. I hate to do this, but unfortunately, I do need to end. I'm gonna be raiding someone. Just a second. I'm gonna be raiding someone. There's a person who is doing. I'm not sure what they're doing, but it's some kind of co-working thing, and their name is Chi Nymphia. So we're gonna go raid this person. Okay, so I've just muted their thing temporarily. All right, so I'm gonna start up the raid, dude. I wish I could carry on streaming, but like I need to end. It's about that time for me. Encoders, once again, thank you very much for the raid. I appreciate it. Um, Jara, Edu Jara, thank you for the follow. Anyone who might have been lurking in the stream, thanks for hanging out. I appreciate it. I'm gonna try and stream again tomorrow. I want to stream again tomorrow, so I'm gonna try my best. But yeah, that being said, I hope you guys have a nice day, and I'll see you all next time. Peace.